Hello everyone, and I hope you enjoyed my last video on finding the centre of mass of a lamina. And the lamina was in the shape of a right angled triangle, a continuous distribution of mass. To remind you what we did, because this is relevant for this video, but check the last video as well, just to remind yourselves what happened. What we had a formula for a continuous mass. And the formula was the integral from a to b x dm for the x coordinate and y dm for the y coordinate. And what we did is we found an expression for dm. And dm, if you remember, was sigma, the area density, times f of x, the function which we're integrating over. In this case, for the triangle, it was a straight line, times dx, and we substituted that in for dm, and we had a ready to integrate expression provided we knew what f of x was. And for the triangle, it was a straight diagonal line, so it was simple. And similarly for the y coordinate, you can go back to that discussion. Now in this video though, I'm going to find the centre of mass of a semicircle. Now the semicircle also has a function, f of x, that depends on x, but it's not a straight line, it is a quadratic. Therefore it's got a squaring term in it. So the question is, well, what is the f of x for a semicircle? Well, first thing I'm going to do is I'm going to draw an xy plane, and draw on the xy plane an arbitrary circle centred on the point hk. Then I write down my equation of the circle for that point with radius r. Well, that's going to be x minus h all squared plus y minus k all squared is equal to r squared, something you're familiar with. But that's not a convenient place to evaluate this problem. First of all, it's a circle, so how do I make it into a half a circle? Well, what I'm going to do is you solve it for y. When you solve it for y, you take the square root of y squared, you've got two answers. You've got a plus and negative answer. I'm going to use the upper half circle, the upper semicircle. So I'm going to get rid of the minus sign, just ignore that. Then I'm going to make the origin, I'm going to put my semicircle and put it at the origin, where it's got a centre 0, 0, which means hk is 0, 0. Then I end up with my function f of x is equal to the square root of r squared minus x squared. Now remember, this is going to be the y coordinate, so I have to use my y formula, which will be 1 over a integrated from negative r to r, y over 2 times f of x dx, where remember f of x is simply y. So when I put my f of x in, my square root of r squared minus x squared, I end up with a very, very simple integral to integrate. And you can actually see, you can go through the simple steps yourself, I'm assuming you'll know that, and then you have the equation, you have the expression for the semicircle centre of mass, which in this case will be 0, 4 over 3 times r over pi. Now if I wish to prove that the x coordinate for a centre of mass is equal to 0, I have to use my x coordinate formula for a centre of mass, which is equal to 1 over a negative r to r integrating x f of x dx, where f of x is equal to r squared minus x squared all square rooted. So I need to substitute this in. So my integral becomes 1 over a negative r to r x into r squared minus x squared square rooted dx. Now, let's see if we can save ourselves some work. X into r squared take away x squared square rooted is an odd function, because f of negative x is equal to negative f of x. What does that mean? Well, it means it's symmetrical about the x-axis. So if I integrate it between negative r and r, where r can be any number, I'm always going to get the answer 0. I've plotted the graph here on Desmos, so you can see the symmetry here. And that's all we need to do. Make the observation, we have proved it. So the coordinates for a centre of mass of a semicircle in this orientation will be 0, 4 over 3 times r over pi.